Introduction to Parametric Equations. Let's start by laying a foundation. Many functions are written in the form y equals f of x, where y is a function of the x variable. Or more simply, you plug in an x and you get a y. But sometimes that is too limited to describe the full story of an object in motion that changes over time, or a curve that loops, crosses itself, or backtracks. In those cases, we can use parametric equations. X is equal to x of t, so x is a function of t, and y is equal to y of t, so y is a function of t. Both x and y are written in terms of a third variable called a parameter, which is often t to represent time. So the set of points to represent a parametric curve in the xy plane is defined by the point x of t, comma, y of t. Let's break it down further. Why do we use parametric equations? First, to describe motion. If something is moving, its x and y positions are changing over time. So for example, we could have x of t is equal to 3t and y of t is equal to 2t plus 1. This is a set of parametric equations, and this tells you exactly where the object is at any time t. We can look at the x component separate from the y component for different times t. Another reason to use parametric equations is to describe curves that can't be written as functions, because we know some curves don't pass the vertical line test, and that's what needs to happen to be a function. So for example, here are some interesting sets of parametric equations. X of t equals t cosine t, and y of t equals t sine t. When you graph this as a set of coordinate points, you end up with this really interesting spiral, which definitely doesn't pass the vertical line test. If we draw a vertical line in different places, we're going to cross more than one time. And x of t equals sine of 2t and y of t equals sine of 3t creates this really interesting curve, which again is not a function. It doesn't pass the vertical line test. And a third reason why we use parametric equations is to control how a graph is drawn. So with parametric equations, you get to control the direction an object moves. So if we change the signs of x of t and y of t, or we reverse the parameter, if we change t to negative t, we can change the direction the object moves. We can change the speed it travels by scaling t, by multiplying t by a scalar. So we could have x of 2t and y of 2t. And even when the object stops or loops back. So we can restrict the interval for t values that we're going to substitute in, or use periodic functions like sine or cosine. Let's take a look at an example. Graph the curve defined by the parametric equations x equals 2t and y equals t squared minus 1. So each value of t, the parameter, gives you a point, x comma y. Indicate the direction of motion. So here, instead of just having an xy table, we have a txy table. We're going to substitute in values of t into x and into y. So here, x equals 2t means we're going to multiply t by 2, or we're going to double t every time. So let's complete this first column. Negative 3 times 2 is negative 6. Negative 2 times 2 is negative 4. Negative 1 times 2 is negative 2. 0 times 2 is 0. 1 times 2 is 2. 2 times 2 is 4. And 3 times 2 is 6. Now, to find the y values, I'm going to substitute in each of the t values into t squared minus 1. So I'm going to square each of these values and then subtract 1. So negative 3 squared is 9, and 9 minus 1 is 8. Negative 2 squared is 4. 4 minus 1 is 3. Negative 1 squared is 1. 1 minus 1 is 0. 0 squared is 0. 0 minus 1 is negative 1. And then 1 squared is 1. 1 minus 1 is 0. 2 squared is 4. 4 minus 1 is 3. And then 3 squared is 9. 9 minus 1 is 8. So now we're going to go ahead and plot these coordinate points. So we have the coordinate point negative 6, 8. Negative 6, 8. And then we have negative 4, 3. So we'll plot that point. And then negative 2, 0. So that is an intercept. And then 0, negative 1. So we have another intercept. We had an x-intercept and a y-intercept. I'm going to go ahead and pause right here for a second because I want to go ahead and think for a brief moment about the direction of motion. So we substituted in values for t, starting from negative 3 to 3, and we graphed those points in order, and so the direction of motion is going to be going down as I follow this curve so far. Now, the next point at 2, 0, I'm going to start moving in an upward direction, and then I have 4, 3, and then finally 6, 8. All right, now, I just arbitrarily chose these t values from negative 3 to 3, but there was no restriction on the parameter t. So if I would have plugged in negative 4, negative 5, or 4 and 5, the motion would have continued. So in other words, it's going to be going down and then up on the other side. So this continues on and forms a parabola. So this set of parametric equations here forms a parabola. In this follow-up question, we're asked, what would the graph look like if we restricted the parameter to 0 is less than or equal to t is less than 2? So we're including 0, but not including 2. And we have the same set of parametric equations. So let's go ahead and remind ourselves of our t, x, y table values, but only for t values between 0 and 2. So when I substituted in 0, I had 2 times t, so 2 times 0 is 0, and then 0 squared minus 1, so negative 1. Here, 2 times 1 is 2, and then 1 squared minus 1 is 0. 2 times 2 is 4, and 2 squared minus 1 was 3. So we're going to go ahead now and plot the point at 0, negative 1. And I am going to put a filled in circle there because the t value was included in the parameter. Now my next point is at 2, 0. And so my direction of motion is increasing here. And my next point is at 4, 3. But there I'm actually going to put an open circle because 2 is not included. So we just had t is less than 2. So I'm going to go ahead and continue the direction of motion, but it should not be a filled in circle right there at 4, 3. So this is what the graph would look like if we restricted the parameter. On this example, we could have turned the parametric equations x equals 2t and y equals t squared minus 1 into a Cartesian equation. A Cartesian equation uses x and y's only. So basically, this is called eliminating the parameter. And another way to say Cartesian equation is sometimes rectangular equation. All right, so let's go ahead and work through this process. What we're going to do is we're going to look at our parametric equations, and we're going to decide which one, if any, is easily solved for t. So here, x equals 2t and y equals t squared minus 1. So here, I can solve pretty easily for t in x equals 2t. So if I start with x equals 2t and divide both sides by 2, then I will get x over 2 is equal to t. Now, I substitute x over 2 into the t of the other equation. So if I do that, I'll get y is equal to x over 2 as a quantity squared minus 1. And if I square the numerator and denominator, I get x squared over 4 minus 1, or y equals 1/4 x squared minus 1. So notice I have an equation in just x and y. So I have y as a function of x, and it's a parabola, which is what the graph looked like when we graphed it as a set of parametric equations. Now, on this example, just as a quick note, if we were to have tried to solve for t in the y equation, so if I have y equals t squared minus 1, I could add the 1 to the other side. But in order to solve for t, when I take the square root of both sides, I'm going to get plus or minus the square root of y plus 1. So it's going to break off into these two branches. So this is not the method that we want to use to eliminate the parameter. Here we got a nice clean Cartesian equation, or equation in just x and y. So getting a Cartesian equation by eliminating the parameter can help us recognize the graph and analyze it quicker, including differentiating and integrating. But eliminating the parameter is not always possible. So for example, x equals t minus natural log t and y equals t squared plus sine t. I cannot cleanly solve for t in either of these equations, so eliminating the parameter is off the table. For this example, we want to graph x equals 2 cosine t, y equals 4 sine t, where t values are between 0 and 2 pi, including 0 and 2 pi. Then we're going to describe the graph, then eliminate the parameter and write the Cartesian equation. All right, so this is going to be some practice in trig. We are substituting in 0, pi over 6, pi over 4, pi over 3, pi over 2, pi, and 3 pi over 2 into both sine and cosine. So we'll start by substituting these into cosine. Cosine of 0 is 1, times 2 is going to give us 2. Cosine of pi over 6 is radical 3 over 2. So if we multiply that by 2, this is just going to be radical 3. Cosine of pi over 4 is rad 2 over 2, but if we multiply that by 2, this is just rad 2. Cosine of pi over 3 is 1 half. 1 half times 2 is 1. Cosine of pi over 2 is 0. 0 times 2 is 0. Then we have cosine of pi is negative 1 times 2. That's negative 2. And cosine of 3 pi over 2 is also 0. Now, for the y values, we're plugging into 4 sine of t, so we'll plug into sine of t and then multiply by 4. Sine of 0 is 0. 0 times 4 is 0. Sine of pi over 6 is 1 half. 1 half times 4 is 2. Sine of pi over 4 is radical 2 over 2 times 4. This is going to be 2 rad 2. Sine of pi over 3 is radical 3 over 2. So 4 over 2 is 2. So we're going to have 2 rad 3 on this one. Sine of pi over 2 is 1. So we're going to have 0, 4. And then sine of pi is 0. 4 times 0 is 0. And then sine of 3 pi over 2 is negative 1. So 4 times negative 1 is negative 4. All right. So now let's go ahead and plot these points. So let's go ahead and plot 2, 0. This corresponds to t equal to 0. And then the square root of 3, 2. So let's approximate the square root of 3, which is about 1.72. So 1.72 approximately is right here. And then rad 2 times 2 rad 2. Rad 2 is 1.4. So 2 times 1.4 is like 2.8. So we have 1.4, 2.8. This is getting a little ugly here. All right, move that one over a bit. Then we have 1 times 2 rad 3. So about 1, 3.14. So we'll say about here. And then finally 0, 4. So that is a y-intercept. So let's go ahead and start to connect these points here as nice as I can. All right, and then from here, it jumps all the way because we didn't plot points between pi over 2 and pi. It jumps all the way to negative 2, 0. Well, hopefully we can sort of justify that it's gonna continue on with that same shape the symmetry along the y-axis is going to occur. And then we have 0, -4. So we're down here. And then, what we didn't substitute in was 2 pi, or did we? Because substituting in 0 is the same as substituting in 2 pi. So we're going to end up back where we started at 2, 0. So we'll go ahead and continue and finish off. So we started, this point corresponded to t equals 0, and this point corresponded to t equals pi over 2, and this was t equals pi, and then t equals 3 pi over 2, and then we got back to t equals 2 pi here. So describe the graph. This graph, if I would have drawn it a little bit nicer, is an ellipse. So this is an ellipse. And the next thing that we want to try to do is eliminate the parameter. But the process for doing this is different than the last one. So we're not going to go ahead and solve for t as we did in that previous example. So because we have these trig functions involved, we kind of want to think back to what relationship do we already know involving sine and cosine that forms an equation. So in other words, I should hopefully already know that sine squared t plus cosine squared t is equal to 1. All right, well, if I know this is true, then over here, let's go ahead and solve for cosine t and sine t. So if I go ahead and divide both sides of this equation by 2, I will get that cosine t is equal to x over 2. So I can come over here and replace cosine t with x over 2. And since cosine is squared, I have to square x over 2. So again, sort of that scratch work. I had x equals 2 cosine t. I'm dividing both sides by 2. So x over 2 is equal to cosine t. And then in a similar way, y is equal to 4 sine t. So if I divide by 4, y over 4 is equal to sine t. So I'm going to replace sine t right here with y over 4 and square it. And that's equal to 1. So look what I have, an equation involving x and y. I have a Cartesian equation. Let me just simplify it a little bit. So I have y squared over 16 plus x squared over 4 is equal to 1. Here is my Cartesian equation, my equation that involves x and y. And if you remember from a precalculus class when learning about conic sections, this does graph an ellipse centered at the origin. Now, the last question down here, what would happen if we let our parameter interval be 0 is less than or equal to t is less than or equal to 4 pi? So basically what's going to happen here is we're going to go ahead and go around one more time. I'm going to describe that by saying the ellipse would repeat. So here we said this was from 0 to 2 pi, and then it would basically go around again one more time. Given the following parametric equations, intervals of a particle in the xy plane, find the related Cartesian equation and graph it. Then indicate the portion of the graph traced by the particle and the direction of motion. So I have x equals negative radical t, y equals t, and t values are greater than or equal to 0. Well, t values have to be greater than or equal to 0 because we're substituting them into x, which is a square root function, and we can't have any negatives underneath the square root. Let's go ahead and find the Cartesian equation, or let's eliminate the parameter. This one's actually pretty nice because I already have y is equal to t. So I can go ahead and substitute for t, y. So in other words, I have x is equal to negative radical y. This is my Cartesian equation. However, I'm used to graphing functions that are y equals some function of x. So what I'm going to do is solve this equation for y. I'm going to multiply by the negative. So I have negative x is equal to the square root of y. And then I'm going to go ahead and square both sides to solve for y. So I'm going to have y equals x squared. I'm going to have y equals x squared. y equals x squared is a full parabola. So here, if I were to graph this, y equals x squared, I would get this parabola with the vertex at the origin. So I'd get something like this. This is y is equal to x squared. But this doesn't take into account the fact that there is a restriction on the parameter t. T values had to be greater than or equal to 0. So what that means is that the only outputs for x, so if I let t values be greater than 0 here, the only outputs for x are negative values, because here I would get these outputs of the square root of t times a -1. So the restriction on x is that x values actually have to be less than or equal to 0. So the Cartesian equation is y equals x squared with the restriction that x values are less than or equal to 0. So here's the x value 0. I actually only want the parabola on the left side. So I'm going to go ahead and erase this side over here. That's not part of my graph. So it's just going to stop right there at the origin. And now, what's the direction of motion here? Well, let's think about, back to our parametric equations for a second. If I start substituting in 0, I'd get negative the square root of 0, so I'd get 0, 0. And then if I plug in, let's say 1, I'm going to get negative the square root of 1. That's -1, 1. So -1, 1 is right here. And so my direction of motion is going to be going this way into quadrant 2. So we answered all parts of the question. We found the Cartesian equation. It did have a restriction now on x. We graphed it. We indicated the portion traced by the particle, and then direction of motion. We're going to follow that same set of instructions, but this time I have x equals a sine t, y equals a cosine t for t values between 0 and 2 pi, including the endpoints. So if we want to eliminate the parameter, because it involves sine and cosine, again, what we're going to do is we're going to go ahead and start with an equation that we know already that involves sine and cosine. So we're going to start with the fact that sine squared t plus cosine squared t is equal to 1. And then on our original equations, we'll go ahead and divide both of those by a. So we'll get sine t is equal to x over a. So I have x over a squared plus, divide both sides by a here, y over a is equal to cosine t, which is squared, is equal to 1. And then I have x squared over a squared plus y squared over a squared is equal to 1. Notice that here the denominators are the same. So what I can do is clear fractions. I can multiply the left and right side by a squared. So this a squared would distribute and cancel in both cases. So I get x squared plus y squared is equal to a squared. So what did we get? We got a circle. This is the equation for a circle. The center of this circle is 0, 0, and the radius is a. Normally it's x squared plus y squared equals r squared, where r is the radius. So here the radius is a. So let's go ahead and graph this. We have a circle that is centered at the origin. I'm going to go ahead and draw a circle here and move it a little bit. So I have a circle that's centered at the origin, and then its radius again is a. So in every direction, I'm going to have a, negative a. So here is my circle, and let's just think about that direction of motion. So if we substitute in 0, sine of 0 is 0, so the x component is 0. And then if I plug in 0 here, cosine of 0 is 1 times a is a. So my starting value is at 0a. So this guy's actually going to start up here. This corresponds to t equals 0. And then let's think about what happens when I substitute in, let's say, pi over 2. So I'm going to go ahead and erase this for a second, just to think about this clearly. Sine of pi over 2 is 1. So my x coordinate is just going to be a times 1. So my x coordinate is a, and then cosine of pi over 2 is 0. So this is going to be 0. So I'm going to have uh, a 0, which is this point right here on the x-axis. So this is going to correspond to when t is equal to pi over 2. So my direction of motion, in other words, is in this clockwise direction. All right, so we answered all parts of the question. To wrap up this introductory section, let's take a look at the fact that any function y equals f of x can be parametrized by letting x equal t and then y is equal to f of t. So in other words, if we have the parabola y equals x squared, so this is y is a function of x, but we somehow want to introduce a parameter t, what we can do is we can go ahead and let x equal t, and then we just go ahead and replace the x in the function of x with a t. So then y is equal to t squared. So that's one really basic, simple way that we can parameterize any y equals f of x function. So here in this example, let's parameterize y equals x cubed minus x in at least two different ways. So let's start with sort of the boring way. Let's let x equal t, and then y is going to be equal to t cubed minus t. So we let x equal t, and then wherever there was an x in the original function, we're going to replace with a t. Because remember, to eliminate the parameter, we can just go ahead and now replace t with x, and then boom, we get back to the original. So this is one possibility. But another possibility is we can let x equal 2t. And then y would be equal to 2t cubed minus 2t. Or y would be equal to 8t cubed minus 2t. So this is another set of parametric equations that would parameterize this cubic function.